Hello friends, so welcome to lecture series on matrix analysis with applications. So the next lecture is on rank of a matrix. What do you mean by rank and how it is important to solve system of linear equations, we will see in this lecture and in the next lecture. So before defining rank of a matrix, let us see what do you mean by linear dependent or linear independent of elements of Rn or Cn. So let V1, V2 up to Vk, let us suppose these are k elements of Rn or Cn. What do you mean by Rn? Rn means all those x1, x2 up to xn such that xi belongs to R for all I. That means Rn is simply a set of n tuples such that each xi belongs to R. Now, if you think about Cn, then Cn is simply all x1, x2 up to xn such that xi belongs to set of complex numbers for all I. Okay. Now, in this definition, this V1, V2 up to Vk are the elements or vectors, we also call it vectors in Rn or Cn. Okay. That means each Vi is consists of set of n tuples which is in either in Rn or in Cn. Then these elements or vectors are said to be linearly dependent or LD if there exist scalars alpha 1, alpha 2 up to alpha k, not all 0 such that alpha 1 V1 plus alpha 2 V2 plus and so on up to alpha k Vk equal to 0. Okay. And if the equation 1 is satisfied only for alpha 1 equal to alpha 2 equal to alpha k equal to 0, that is all alpha is a 0, then these vectors are called linearly independent. Now, let us understand what do we mean by this. Now, you have vectors, this is V1, V2 up to Vk. Let us suppose this belongs to Rn. Each Vi belongs to Rn. Okay. Now, you take alpha 1 V1 plus alpha 2 V2 plus and so on up to alpha k Vk. This is called linear combination of V1, V2 up to Vk. These alpha i's are some scalars, some constants. Okay. Now, this you change alpha i's, this V will change. Okay. If you change alpha I, you vary alpha i's, this V will change, but all V are simply the linear combination of elements of Vi's. Okay. Now, if alpha 1 V1 plus alpha 2 V2 equal plus and so on up to alpha k Vk equal to 0, this implies alpha I equal to 0 for all I from 1 to k, then we say that V1, V2 up to Vk are linearly independent. That means you take a linear combination of V1, V2 up to Vk, put it equal to 0 and there exists only one solution which is alpha equal to 0 for all I. That means V1, V2 up to Vk are linearly independent vectors or elements. Okay. Now, if we are taking alpha 1 V1 plus alpha 2 V2 plus and so on up to alpha k Vk and this equal to 0 implies there exists at least one alpha I which is not equal to 0. Okay. Then V1, V2 up to Vk are called linearly dependent. Okay. Let us suppose let us suppose that alpha I which is not equal to 0 is alpha p, okay, is alpha p. So, let alpha p is not equal to 0 where p is between 1 to k. P is any element between 1 to k, okay. Then you leave alpha p Vp in this side and all the remaining terms over here on the right hand side. So, this will be minus alpha 1 V1 minus alpha 2 V2 and so on, minus alpha p minus 1 Vp minus 1 minus alpha p plus 1 Vp plus 1 and so on, minus alpha k Vk. And since alpha p is not equal to 0, so you can always divide by alpha p. So, this implies Vp will be equal to minus alpha 1 alpha p V1 minus alpha 2 upon alpha p Vp and so on, minus alpha p minus 1 upon alpha p Vp minus 1 minus alpha p plus 1 upon alpha p Vp plus 1 minus alpha k upon alpha p into Vk. So, yeah, okay. So, so that means what? This is alpha 2. So, that means what? That means if vectors are linearly dependent, then there exists at least one vector which can be expressed as linear combination of remaining vectors. So, you can always put it some beta 1, you can always take it some beta 2, you can always take it some say beta p minus 1 and so on. So, what I want to say that if vectors are linearly dependent, then there always exists at least one vector or one element in that set which can be expressed as linear combination of remaining vectors. And if vectors are linearly independent, then none of the vector can be expressed as linear combination of remaining vectors. Okay. Now, let us discuss this thing by few examples. So, what do you mean by linearly independent or dependent vectors? Let us discuss all these things. So, the first problem is this is 1 2, then 0 2 and then 3 4. These vectors are in R2, okay. These vectors are in R2. We have to see whether this set of vectors are linearly independent or dependent. Now, you can simply see here, if you see the by observation, you can always see that 3 comma 4 can be expressed as 3 times 1 comma 2 plus either it is 0 comma 2, you see it is 3 times, that is 3. Now, you want 4, so it is 6 minus 2, okay, it must be 1. It is 6 minus 2 is 4, okay. So, we have expressed this vector 3 comma 4 as a linear combination of these two vectors. So, what does it mean? It means that these vectors are linearly dependent. So, this is linearly dependent LD, this set is LD, okay, because we have expressed one vector as a linear combination of the remaining vectors. Other way out is you take a linear combination of these vectors, okay, and put it equal to 0. So, what does it imply? It implies it is alpha 1 plus 0 plus 3 alpha 3 comma it is 2 alpha 1 plus 2 alpha 2 plus 4 alpha 3 equal to 0 0. So, this implies this is equal to 0 0 means each component is 0, that means alpha 1 plus 3 alpha 3 is equal to 0 and 2 alpha 1 plus 2 alpha 2 plus 4 alpha 3 equal to 0. Now, this is, you see, we are having two equations and there are 3 unknowns and equation is homogeneous, right hand side is 0, okay. So, you can arbitrarily choose any value of alpha 3, may not be 0, okay. Then you can find out alpha 1 and alpha 2. So, that means there exists some alpha which is not equal to 0, and that means that this set of vectors are linearly dependent, Okay. Now for a second problem, if you see a second problem 2 1 0, it is 1 0 2 and 0 1 2. Okay. These are in R3, and you have to see whether this set of vectors are linearly independent or dependent. So, you take the linear combination of these vectors, okay, put it equal to 0. Okay. So, this implies 2 alpha 1 plus alpha 2 equal to 0, then alpha 1 plus alpha 3 equal to 0, and then 2 alpha 1 alpha 2 plus 2 alpha 3 equal to 0. Okay. So, what does it imply? From here we are getting alpha 2 as minus 2 alpha 1. When we substitute it here, we are getting from here it is minus 2 alpha 1 plus alpha 3 equal to 0. That means alpha 3 is equals to 2 alpha 1. Okay. And when we substitute it over here in this equation, alpha 1 is alpha 1 and alpha 3 is 2 alpha 1, it is equal to 0. So, this implies alpha 1 equal to 0. Okay. And when you substitute alpha 1 equal to 0 here, from here we are getting alpha 2 equal to 0, and from here we are getting alpha 3 equal to 0. So, that means we are getting only one solution, which is a 0 solution. That means all alpha is a 0. Alpha 1 is 0, alpha 2 is 0, alpha 3 is 0. It is the only solution of this equation. That means these vectors are linearly independent. Now, if you take this set 0 0 0, 1 2 3 and 4 5 3 4 5, the next example, next problem. Now, this is clearly linearly dependent. Why it is linearly dependent? Because this vector 0 0 0, this 0 0 0 can always be expressed as 0 times 1 2 3 plus 0 times 3 4 5. That means one of the vector of this set can be expressed as linear combination of remaining two vectors. This means set is LD, set is linearly dependent. Now, if you see the next problem, it is 2 3 4, then minus 1 4 2, then 1 7 6. Okay. Now, you have to see whether this set is Li or LD. So, you take linear combination of these three vectors, put it equal to 0, and if you find only one solution, that is all alpha is a 0, that means these vectors are linearly independent, otherwise linearly dependent. One thing you can easily observe that this vector is equal to the sum of these two vectors. See, 2 minus 1 is 1, 3 plus 4 is 7, 4 plus 2 is 6. That means 1 7 6 is equal to 1 times 2 3 4 plus 1 time minus 1 4 2. So, that means one vector can be expressed as linear combination of the remaining vectors. This clearly means set is LD, set is linearly dependent. Okay. So, in this way we can check whether set is linearly dependent or independent. Now, we will see some properties of dependent or linearly independent sets. The first property is any set containing 0 element is always LD. This is very easy to show. You see, if we are having any set containing 0 element, then that 0 element can always be expressed as linear combination of the remaining vectors, where scalars are all 0. Okay. So, since this 0 vector can be expressed as linear combination of remaining vectors, so the set is clearly LD. As we have also seen one of the example, you see we have already seen in this example, the third example, that why this set is LD, because this 0 0 0 can be expressed as 0 times this plus 0 times this. That means this vector 0 vector can be expressed as linear combination of remaining two vectors. Okay. The next property is any set S which is a subset of Rn containing n plus 1 or more elements is always LD. Okay, this is easy to prove. You see, You see we have some set say V1, V2 up to Vn up to Vn plus k suppose, and all Vi's are in Rn. Okay. So, this is a set containing n plus 1 or more elements. K is greater than or equal to 1. So, this set is containing n plus 1 or more elements, and each Vi's, you see if we are talking about V1. So, V1 is in Rn, that means it is V11, it is V12 and so on up to V1n. And similarly, if you talk about Vi, so Vi is simply Vi1, Vi2 and so on up to Vin for all I. Okay. Now, if you take the linear combination of this vector, so V alpha 1 V1 plus alpha 2 V2 and so on up to alpha n plus 1 V alpha n plus p Vn plus p equal to 0. Now, when you substitute V1 from here to here, similarly V2, which is a n tuple set of n tuples, okay. Similarly Vn plus p. Then when you multiply with alpha 1, multiply V2 by alpha 2 and so on, you will get n equations with n plus p unknowns. Okay. P n plus k, sorry, it is n plus k, here it is k, okay. Here also it is k. So, we are getting n equations with n plus k unknowns, k is greater than or equal to 1. So, more unknowns and equations are less, that means many solutions, and many solutions means there exists non-zero solution, and non-zero solution means set is LD, set is linearly dependent. So, this set is always LD. Okay. The third property is, if the set is LD, then any superset of it is also LD. Okay. This is again easy to show. You see, if we have a set say V1, V2 up to say Vp, say this set is LD. So, if this set is LD, that means there exists some Vk where k is between p to 1, such that this Vk can be expressed as linear combination of remaining vectors. Okay. Alpha p Vp. Now, take a superset of this set. Say superset is V1, V2 up to Vp and so on up to say Vp plus m. Take a superset of this set containing elements more than this, containing this set and some more elements. Now, if alpha k can be expressed as linear combination of the remaining vectors, then this alpha k can also be written as alpha 1 V1 and so on up to alpha k minus 1 Vk minus 1 plus alpha k plus 1 Vk plus 1 plus alpha p Vp plus 0 times remaining vectors. Okay. That means linear combination of remaining vectors. So, this set will also become linearly dependent, because we have expressed one element Vk which is in this set and can be expressed as linear combination of remaining vectors. Okay. So, this set is also LD. So, we have shown that if you have any set which is LD, then any superset of this set is also LD. Okay. The next property is, if a set is Li, then any subset of it is also Li. If it is not, if any subset of it is not Li, then it is LD, and if it is LD, then the superset of this set will also be LD, however it is Li. So, this contradict statement 3. Okay. So, therefore, if a set is Li, then any subset of it is also Li. Now, come to the rank of a matrix. How we define rank of a matrix? Say we are having a matrix of order m cross n. Then the rank of matrix A denoted by Ra or rank of A is defined as the number of non-zero rows in the echelon form of a matrix. We have already discussed echelon form of a matrix. Now, number of non-zero rows in the echelon form is called its rank, or it can also be defined as maximum number of linearly independent rows or column of the matrix A. Okay. If you have a matrix, say A11, A12 and so on up to A1n, A21, A22 and so on A2n, it is of order m cross n. Now, you take the first column, say C1 as a one vector, the second column as a second vector, and the third, this mth column as a mth vector. Okay. Okay. Sorry, it is n. Okay. If this number of linearly independent vectors, number of independent columns is the rank. I mean, we are taking the one column as a one vector, the second column as a second vector, the nth column as a nth vector. Similarly, if you take the row, the first row as a first vector R1 and the mth row as a mth vector. So, the number of linearly independent rows or columns considering one column as a one vector or considering one row as a one vector. Okay. So, number of rows or number of linearly independent rows or columns is the rank of the matrix. Okay. Now, let us discuss few examples. You see, now this is the matrix A. Now, this is the echelon form of some matrix. It is clear because you see the first leading non-zero element is 1 in the first row, and in the below this all elements are 0. In the second row, the first leading non-zero element is 2, and below this all elements are 0, and all rows containing only 0 element are at the bottom of the matrix. Okay. So, now how many number of non-zero rows it is having? It is having only 2 rows, first row and the second row. So, that we can say the rank of this matrix is 2. Okay. We can also say like this, you see this vector 1 2 1 can never be expressed as alpha times 0 to 4. Okay. So, these two vectors are linearly independent. So, maximum number of linearly independent rows which this matrix is having is only 2. Okay. So, rank of this matrix is 2. Now, see here, if you have this matrix, the first row is 2 2 3, the second row is -2 -2 -3, third row is 6 6 9. Now, if you multiply the first row with -1, you will get the second row. That means the second row is simply -1 times the first row. Okay. So, that means these two rows are linearly dependent. Similarly, if you multiply this first row by 3, you will get the third row. That means this row and this row is also dependent. So, how many maximum number of linearly independent rows which this matrix is having? Only one, that is 2 2 3, because other two rows are linearly dependent on the first row. So, maximum number of linearly independent rows which this matrix is having only 1. So, the rank of this matrix is 1. You can also find the echelon form of this matrix, and then you can see the number of non-zero rows which this matrix is having. Now, let us find the echelon form of these matrices. I mean echelon form and then the rank. Now, what is the matrix you are having? It is 1 3 -1 2 and 2 1. Let us find the echelon form of this matrix. The echelon form will be, you see 1 3. You will make 0 here with the help of this. So, how you will make this? In R2 you will apply R2 plus R1. So, that will be 0, this is 5. You will again make 0 here with the help of this, that is R3, you will take R3 minus 2 times R1. So, that is 0, this minus 2 times this, and this minus 2 times this is minus 5. Okay. Now, in this is the first non-zero element, you will make 0 in the bottom. So, in the third row again you will take R3 plus R2. So, what will the final form? 1 3 0 5 0 0. So, what is the echelon form of this? This is the echelon form of this matrix, and what is the rank? Rank will be simply rank of this matrix. If this matrix is A, the rank of this matrix is simply 2, because number of non-zero rows are 2. Okay. In fact, if it is this order is 3 cross 2, you see the order of this matrix is 3 cross 2. This is 3 cross 2. So, rank can never be more than 2. Okay. Because whatever element you are having here, you will always make 0 with the help of this to convert this matrix into its echelon form. So, maximum linearly independent rows or maximum non-zero rows which this matrix is having is only 2. Okay. It may be less than 2 also, but the maximum is only 2. You see, if you are having this type of matrix 1 2 2 4 and then 3 6, what is the echelon form of this matrix? 1 2 0 0 and then again 0 0. So, the rank of this matrix is simply, if this is B, the rank of this matrix is simply 1. Okay. So, what I want to say that if a matrix having an order m cross n, the rank of this matrix can never exceed n and similarly can never exceed m. So, it will be always less than or equals to minimum of m or n. Okay. Now, you have second example, suppose it is 2 minus 1 4 5 4 2 2 1. So, it is having 2 rows and 4 columns. Of course, by simply seeing the order of the matrix, I can say that rank of this matrix, if it is A, then rank of this matrix is always less than or equal to 2. This I can say surely, because rank of a matrix is always less than or equal to minimum of m or n, because rank can never exceed m and can never exceed n. Now, the echelon form of this matrix is 2 minus 1 4 5. You have to make 0 here with the help of this to find its echelon form. So, this row in R2 you will make a elementary row transformation, R2 minus 2 times R1. So, it is 0, this minus 2 times this is 4, this minus 2 times this is minus 6, this minus 2 times this is minus 9. So, how many number of non-zeros it is having? It is having 2 rows. So, we can say the rank of A is 2. Okay. Now, the next problem is, suppose we want to find out the conditions on alpha and beta for which this matrix is rank 1, 2 or 3. So, this is also a simple problem, let us try to find it. So, what is the matrix we are having? Matrix is alpha 1 2, it is 0 2 beta, it is 1 3 6. So, first find its echelon form and then only we can say the rank of this matrix A. So, for echelon form, it is alpha and it is 0. So, first you will, because it is a parameter alpha which may be 0 also, we do not know. So, first interchange the third row with the first row. Okay. So, it is 1 3 6, it is 0 2 beta, it is alpha 1 2. We have make R3 with R1, interchange R3 with R1. Now, it is 1 3 6, it is 0 2 beta, you make 0 here with the help of this. So, this minus alpha times this is 0, this minus alpha times this is 1 minus 3 alpha, this minus alpha times this is 2 minus 6 alpha. Now, you will, for the echelon form you will make 0 here with the help of this. Again you will make elementary row transformation 1 3 6 0 2 beta, it is 0, it is 0. What operation you have applied in R3? It is R3 minus 1 by 2 times, it is 1 minus 3 alpha times R2, okay, to make 0 here, and the same operation you will apply here. So, what we will obtain, you see, it is 2 minus 6 alpha minus 1 minus 3 alpha by 2 times beta. So, what you will get, it is 1 minus 3 alpha into 4 minus beta upon 2. So, this element will be 1 minus 3 alpha into 4 minus beta upon 2. Now for which values of alpha and beta rank of this matrix is 1? You see, this element is non-zero. So, rank will always be 2 or more than 2. Rank is either 2 or 3. Rank can never be 1. So, the first one, the answer is for rank 1, no alpha beta, because this case is not possible. I mean, not possible, this case is not possible. For no values of alpha and beta, rank is 1. Okay. Now, for rank 2, now rank of this matrix is 2 if this quantity is 0, and this quantity, because if this is 0, then we are having 1 0 row. Okay. Now, this entire row cannot be 0 because this is 2. Okay. So, rank will be 2 if either alpha is 1 by 3 or beta is 4, and rank of A will be 3 if this is not equal to 0. So, that means alpha should not equal to 1 by 3 and beta should not equal to 4. So, whenever you want to find out echelon form of any m cross n matrix, you first write its echelon form and then try to find its number of non-zero rows. From number of non-zero rows you can find its from number of non-zero rows you can find its rank. Now, we have some properties of rank of a matrix. The first property is rank of only 0 matrix is 0. Only the null matrix has a rank 0. Okay. Of course, rank of a matrix can never be in fraction because it is number of non-zero rows. Okay. Elementary row and column operations of a matrix are rank preserving. That means it does not change the rank of a matrix. If you apply row operations or you apply column operations, it will not alter the rank of the matrix. Rank remain the same because it is maximum number of linearly independent rows or columns. Okay. And hence rank of A is same as rank of A transpose. Rank of C times A, where C is any non-zero scalar, is always equal to rank of A. You see, if you multiply a matrix by a non-zero scalar, it will not change the maximum number of linearly independent rows or columns it is having. So, rank will remain the same. This I have already explained that rank of A is always less than equals to minimum of m or n. Now, if you have a square matrix of order n cross n and rank is n. Now, if rank is n, this means matrix does not have any all 0 row, because order of the matrix is n cross n and rank is n. That means it does not have any, in the echelon form of the matrix, it does not have any row containing all 0 elements, and that means the determinant of the matrix is not equal to 0. Okay. Because we have already discussed this thing that suppose A is a matrix and B is echelon form, B is its echelon form, then determinant of A is some alpha time determinant of B, where alpha is not equal to 0. Okay. So, if echelon form does not have any all 0 row, is a square matrix. Okay. Then determinant is not equal to 0. So, determinant of A will not be equal to 0. Okay. And if determinant is not equal to 0, that means the echelon form of the matrix does not have any row which contain all 0. That means rank of that matrix is n. So, from here we can also conclude that if rank of a matrix is less than n, which is n minus 1, n minus 2 or any other thing. Okay. Then determinant of A is always 0, because if rank of a matrix is less than n minus 1, that means it contains at least one row containing all 0 element. So, determinant of the echelon form of the matrix is 0, and hence the determinant of the original matrix is also 0. Okay. So, these are some of the properties of rank of a matrix. So, thank you.